Okay, so this homework assignment took me about an hour to do. It'll take you probably twice as long, maybe 2 hours total to get through everything while you're studying and learning and everything. So take some time. You should be able to sit down and do it all in one sitting, but it will take some attention, so feel free to break it up into points. But with this guide, it should help you quite a bit to focus and do it a little more efficiently. So let's just go through this. Question 1, if two uncharged objects are rubbed together and one of them acquires a negative charge, then the other one is going to acquire what? So you've got one thing rubbing together. This is a conservation of charge. So one thing becomes negative, the other one has to become opposite charge in order to conserve charge. You're moving electrons around, so there's a finite number of electrons. If you take some money out of your bank account, it's going to be gone. Okay. Question 2. A balloon can be charged by rubbing it with the sleeve of your sweater while holding it in your hand. You can conclude from this that the balloon is what? So generally with problems either here or on the exam, if you see a word you haven't heard of and I haven't said, it's probably not important. So a semiconductor, that is something that we use in circuits. We're not going to talk about that for a while. A Gaussian surface is something we use in E&M and advanced physics, but we don't talk about it, so let's ignore that. So it's either a conductor, an insulator, or a neutral object. Well, the thing about a conductor is it conducts electricity. So if you rub it and charge it up while still holding it, if those electrons can't get off of the balloon into your hand and out of there to re-neutralize the balloon because those electrons want to get away from each other, you can conclude that it isn't conducting electricity. Okay, so it must be not neutral because we've charged it up, so it must be what? All right, number 3, you venture out on a cold winter morning to warm up your vehicle. You have layers of cotton polyester blend clothes on, and from walking on carpeting, you have accumulated a net positive charge. Your car is considered a neutral conductor. As you place your hand near the door handle, so you're not touching it, what happens to the charges of your car? So remember that we've had this before where I brought this charged wand up near a sphere. What ends up happening? You polarize the charge on the conductor. If I removed this and took it away, all the charges would mix back up. Okay, so think about that one. Number 4, a positively charged rod is brought near one end of an uncharged metal bar. The end of the metal bar furthest from the charge will be charged what? And so we have the same thing. You've got a metal bar. You're bringing it to another metal bar. What's going to happen? The electrons are going to be attracted over to that side and end up oppositely charged on the other side. Okay, so delete that. Number 5, in each of the scenarios here, we've got either conductors or insulators, and either a big charge Q or a little charge Q. And the question is, when you let go of these two charges, they're hanging from the ceiling. When you let go of these things, what's going to happen? Are they going to come together after you let them go, or are they going to stay separated? So you're supposed to drag these into the boxes here. Either they come to rest in contact or they come to rest separated. So we've got minus Q and plus Q. So if I look at these charges, they're hanging from the ceiling, right? So there's going to be gravity down, and in the case of these two guys, you've got a electrostatic force that's going to bring them together. So these two will come together and at rest at the end and live happily ever after. And these are insulators, so they're going to keep their charge, but it doesn't matter because they're attracted to each other. For something like this set over here, we've got minus Q and plus Q conductors. They're going to come in contact. They're going to mix their charge together, so they're going to be uncharged, and but still come together because there's not going to be any electric force to repel them. For the conductor, for these guys, for the insulators, when they come in contact, what's going to happen? Since this guy has more charge and this guy has less charge, even though they're oppositely charged, when they come together and get close enough, you're going to get a polarization of the charge, and you're going to have more charge on this one than that one. So you're going to have a little bit of an interesting thing to think about with those guys. And this problem's really good. When you make guesses, it gives you some good hints to talk through that one. So just have some fun with that. Try it out. Number 6, classify each statement according to whether it describes a force, electric force, gravitational force, or neither force. So the electric force, remember, is KQ1, Q2 over R squared. The gravitational force is GM1, M2 over R squared. Remember, gravitational force, for example, is always attractive. It acts on mass. For example, the electric force, it acts on charge. It could also be zero between two objects, but the gravitational force can never be zero, and it can never be a repulsive thing. We haven't found an opposite mass configuration. So anyway, drag those into the boxes they belong. Number 7, a metal sphere has a charge of minus Q. An identical metal sphere B has plus 2Q. The magnitude of the force on sphere B due to sphere A is F. What is it on the opposite side? So you got a charge here, a sphere minus Q, another sphere with 2Q. Okay, so we know that they're going to be attracted to each other. Now, what is the force between them? F is KQ1, Q2 over R squared. Does it matter where you put Q1 or Q2? No. And Newton's third law says for every action there's an equal and opposite reaction. So if the force from one to the other is F, the force from the other on the other must also be the same magnitude. Okay? Equal and opposite reaction. Number 8, we've got an arrangement of charges here, and let's just take a look at this. We've got a positively charged Q in the center, and then plus Q minus Q, plus Q minus Q. And the question is, what direction is the net force on the center charge? So on the center charge, we're going to experience a force this way from that guy, because the line connecting them there, and they're the same charge, so we're going to have an opposite force. We're going to have a force this way, which is going to perfectly cancel out because these two are the same charge. And we're going to have the same thing. We're going to be attracted to that one and attracted to that one. And they'll all cancel out. So our vector sum of everything, cancel, 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 means that we're going to have no force. And so you should drag the no force up to there. Okay? Now for the other cases, this part, let's move this Q up to there. What's the net force going to be? So let's put our plus charge and pretend our plus charge is sitting there instead of here. Okay, so we're going to feel a big force this way because we're much closer to this force now. We're going to feel a little force that way from this guy because we're further away from it. 1 over R squared is further, so our force is less. And then we're going to feel a force there from this one and there from that one, attracted to that one, attracted to this one. These are going to have the same magnitude, and their y components are going to cancel out, so there's not going to be any net motion in the y direction, and their x components are going to add to give us an additional push this way. And so our net force, when we consider all the forces, are going to be in this direction. So if our plus charge was sitting there, then it would get accelerated towards the center. Now the question is, how about in this spot? Let's move our plus charge to there. Now we're going to get pushed that way, away from this charge. We're going to be pushed that way, away from this charge, right? And then we're going to be pulled this way towards that one, and pulled this way towards that one. So if you balance all these things out, and you draw your vectors a little bit better than me, you're going to see that your net force is pulled over that way. So anyway, think about all these as you go around, what your force is going to be, and you should find, I'll give you the first 3, something like that. Okay, so just think about those and the lengths of the vectors, and they should play around and add up in that way as you go around the circle. Okay, number 9, for the electric field diagram shown, place charges that would produce the given field. So, for example, we know that positive charges are sources and negative charges are sinks. And so since this is draining, all the charge is draining into this hole, we're going to assume this is a sink. And so that's an electron or a negative charge. Since these are all pushing away from each other, right, then they must be either the same minus sign or either the same plus sign. And how do you know? Well, these are sources, not sinks. And then same thing over here. One of these is a source and one of these is a sink. And depending on the direction of the arrows, you can determine which one's which. Okay, delete that. Number 10, Which diagram correctly indicates the direction of the electric field produced at each point by the positive charge? So we've got a positive charge here at the center, okay? And the question is, we're just imagining fields coming off this thing, and we're picking 3 different points to show the direction and magnitude of the charges. So since it's a positive charge, we know that it's a source, so the arrows should be coming away from it. And so it can't be this one, for example, because these arrows are going towards it. So since it's a positive charge. And then we know that they also have to be pointing away from it. So these guys are at some weird angles, so we know it's not that one. So anyway, work through those, figure out which one it is. Number 11, a certain lightning bolt moves 50 coulombs of charge. How many fundamental units of charge is this? This is just keeping, the charge is in coulombs, and then there's 1 electron per 1.602 times 10 to the minus 19 coulombs. So how many charges is this? You get 50 coulombs, and you could divide by that many coulombs per electron and figure out how many charges on an electron that is. Okay, and let's go to 12. So most workers in nanotechnology are actively monitored for excess static charge buildup. The human body acts like an insulator, so as you're walking across a carpet, it's building up charge because it can't conduct off of it. Or collect 50 nanocoulombs per step. What charge buildup will a workup in a manufacturing plant accumulate if she takes 35 steps? So you're just going to take 35 times minus 50 nanocoulombs, and then that'll give you the number of nanocoulombs for the first one. How many electrons are present in that? So you're going to have that many nanocoulombs, and then 1.602 times 10 to the minus 19 for that. So let's, for example, we can go to Wolfram alpha, and we can just do this 50, I'll show you how to do this, 50 nanocoulombs times 30, what am I doing, 35 steps, okay? So, and then that divided by 1.602 E minus 19 coulombs. And let's see if that nanocoulombs gets interpreted as nanocoulombs, and it does. So then I get 1.092 times 10 to the 13. So that's the number of electrons that would be present there. And then if you can only go 10 to the 12 electrons before you've got a discharge that could harm your device, how many steps could you take before you exceeded 10 to the 12 electrons? So you get 50 nanocoulombs per step. That would be, if you do 50 divided by 1.602 times 10 to the minus 19, you get that many electrons per step, and then you've got 10 to the 12 electrons, so then you can solve for how many steps you can take before you exceed that, okay? Number 13, an electron and a proton are separated by a distance of 1.7 times 10 to the minus 10 meters, roughly the diameter of an atom. What's the magnitude between them? So you can go here, we know it, the Coulomb constant times charge on electron times charge on proton divided by, I'm just going to put 1 centimeter squared. And if I type all that in, that's K Q1 Q2 over R squared. Then I get this 2 times 10 to the minus 24 newtons. Obviously, I made up the distance. You'd have to put in 1.7 E minus 10 meters there, but that would give you the force in newtons. And then what's the magnitude of the gravitational interaction? Well, you're going to actually use the exact same equation, but instead of the Coulomb constant, you're going to use Newton gravitational constant divided by, instead of charge, you're going to say mass on an electron and mass of a proton for the same distance over whatever squared. I get some more newtons here, times 10 to the minus 63. And then the third part is how many times stronger. So you divide those two numbers, and you should get about 10 to the 39 or so. Okay, 34. Question 14. As a skeptical student, you want to test Coulomb's law. For this, you set up a measurement. You got your proton, your electron, 967 nanometers from each other, and you want to know the forces. You find that the forces are what? Well, one's minus, one plus, so they should be attracted to each other, right? And then you also want to find the force, the magnitude of the force. You go back to the problem we just did, retype that same or go back in history to Wolfram Alpha where you had that one and just change the distance to 967 nanometers, and you can get the magnitude of that force. Number 15, what is the force on a charge located at 8 centimeters given that the middle charge, or that Q, is 2 microcoulombs? Okay.